you very much. And I would like to thank the organizers for giving me this opportunity. This is a conference about number theory and non-commutative geometry. In this talk, there will be mostly K-homology, but it will be motivated by examples from number theory. So this is joint work in progress with Haluk Şengün, who's a number theorist currently working at Sheffield, who's interested in Bianchi groups. So these are the examples I'd be looking at. What you should think of is an imaginary quadratic field K, and inside it is its ring of integers. And then you can form PSL2 of this ring, which sits inside PSL2 of C, and this is a group of hyperbolic isometries, so this acts on hyperbolic 3 space. And in general, this quotient, if we call this, no, let's not call this gamma. Gamma will sit inside here as some finite index torsion-free subgroup. In general, the quotient by this group will be some kind of orbifold. I must say I don't understand how to treat that case yet, so we take a finite index subgroup inside here such that you have a nice quotient manifold. So gamma. Yes, exactly. So that we can decently speak about this object. Right. And something I won't say very much about, but these manifolds, the Riemannian invariance of these manifolds correspond to the invariance of the number field, and this is actually a beautiful line of research that I would like to learn more about in the future. I'm going to view this object here, which it's non-compact for these Bianchi groups, always. So there are cusps, and one would like to study compactifications. And the idea I'm going to use is that we're not going to compactify it by adding the cusps, but we're going to non-commutatively compactify it. And this we do by, I will just write H. H will always mean H3. But some of the things I will discuss actually work for general hyperbolic isometry groups. So we take H bar, which is H3 union of P1 of C. This is the usual Gromov compactification of the hyperbolic plane. And the action of this gamma extends to the boundary. So, sorry? Yeah, I mean, sorry, I meant space. The compactification of 3 space, sure. So gamma acts on this boundary, which is a 2-sphere, but the orbits here are dense. So there's no good quotient. And so the idea that is used broadly in non-commutative geometry is to form this cross-product algebra and view it as the non-commutative quotient of the action on the boundary. And what you get is an exact sequence commutative C-star algebras where the middle one is unital. So this is the boundary extension for this compactification, and this is gamma equivariant. So the maps are compatible with the action of the group, and this means we get a long exact sequence in equivariant K-homology. So let me get the indices right. And the maps. Let's go in the other direction. And this sequence, we can simplify it and relate it to some interesting objects. Basically, this group is going to be the k-homology of the algebra C0 of M, because this you can use the Morito equivalence of the cross product with this commutative algebra. Yeah. Exactly. So this is a group we would like to have. This is isomorphic to the k-homology of the boundary cross product. For this, you can use that the action. So the group is not amenable, but the action is, and this means that the max and the reduced cross product for this algebra are the same, and then you use this isomorphism. Yeah. The group is not amenable, but the action, yes, the groupoid is amenable. And then there is this thing in the middle, which will turn out to be the k-homology of the reduced C-star algebra of gamma. And this follows from the fact that, so you can say there's a lemma. You can take the inclusion constant functions. Yes, yeah. So, but this is a bit, no, it's not cheating, but it's easy here because the group is torsion free. So the inclusion here induces an isomorphism in equivariant k-homology, and that's because H bar is equivariantly contractible for finite subgroups of this gamma, but there are none. So this is really easy. This is actually this type of argument I got from papers by Heath Emerson and Bogdan Nika, who looked at a similar construction for the Cayley graph of a group, but here we have a slightly nicer background situation because we're acting on a nice manifold. Okay, so all of this gives us, and say this is very similar to what Emerson and Nika do. The setting is a bit different, but so if gamma is torsion free, there is an exact sequence of 0, K1 of C0 of N, K0 of P1 of C, this cross product, K0 of the reduced C-star algebra, this K0 of C0 of N, into K1 and onto K1. Now this holds quite generally. And the map here I'm not sure. So Emerson and Nika and also Emerson and Meyer relate this to the Euler characteristic of M. So the map looks something like, yeah, you take a Fredholm module and then you send it to the index times the Euler characteristic times the dimension. But the point is, in dimension 3, this map vanishes. So the sequence, so I get two exact sequences. So this is, since the dimension is 3, or in any odd dimensional setting, we get two so-called Gießin sequences. So it just falls apart. the other one, and this will be the one I will be mostly interested in today. I would like to understand the other one as well. But we do one thing at a time. So now we have a nice exact sequence in which the boundary algebra is related to two algebras that are closely related to the geometry of the group. So now we'll say something about what these groups are, because you can, especially in this case, explicitly compute them using some spectral sequence tools. Very similar arguments that work in a p-adic case as well. I found this in papers by Guy and Robertson. So let's see where we are. Right. So there is a spectral sequence. I'm not going to describe it. It's on the last page of Kasparov's long Novikov paper. I think it was refined in collaboration with Skandalis later. But so you can use this to compute the groups, the k-homology group of the reduced C-star algebra and that of the cross product. And the result is that we have this torsion-free group. Then there are exact sequences relating the homology of the group, or the cohomology of the group, to the k-homology of the reduced C-star algebra, the offsetting looks like this. And if you look at the cross product algebra, you get very similar sequences. It's just the coefficients that change. And this is basically due to the k-homology of the sphere. Yeah, well, it's exactly the same, just with Z2 coefficients. So you get these exact sequences, and sorry, come again? Oh, yeah. Yes, yeah. Just so this is just two copies of this group. That's no, the action is trivial. This is just homology with trivial coefficients. And this has to do with the fact that you can explicitly, I mean, it's very well known what the k-homology of the sphere is. So this you plug into the spectral sequence and then reduce to this. The other point is that for these Bianchi groups, H3 is always vanishing. So I actually get an isomorphism of the k-homology of the boundary cross product or the reduced C-star algebra with the first homology group of the group gamma. So H3 vanishes, and this implies that K1 the boundary is isomorphic to H1. No, it vanishes because the quotient is not compact. Yeah. You could also say the boundary map above also vanishes when the quotient is non-compact. And now the question is, what do these isomorphisms look like? So this is what I will discuss now. Yeah. What I will describe for you is take a cocycle here. What do I get here? But we'll actually do it. Yeah. And the construction is really quite natural. So we'll focus on this group, and then later say something about how this works. So indeed, the cycles for this H1 here are just homomorphisms from the group into the integers. Yeah. Sorry, thanks. And these cocycles, well, in the two-dimensional case, there's a relation with modular forms, and in the three-dimensional case, these homology groups are also interesting for that reason. This is what my collaborator originally was interested in, but it turned out that there was quite some work to do to relate this to K-homology in the first place. Yeah, so gamma is piezo2, okay, but well, in the two-dimensional case, it's easy. You take some modular form and you integrate. It's a period map. Yeah, but is this? But is this? I'm not sure if I'm able to give you an example now. I'm also not sure. Is it true that if the group is torsion-free, that it looks like a free group? No, but I was just thinking about SM2. In that case, it's clear that you have a lot of freedom to get. But what about the case that you are considering? I would like to know what type of freedom do you have? How much freedom do you have to choose these homomorphisms? That's a good question. I should ask my collaborator, actually. No. How big is your K1? Yeah. Yeah, so this was also the reason why he was interested in this kind of thing, was because these groups are apparently quite hard to compute. And so a model like this, another thing we would like to think about is the relation to boundary distributions and things, but this is all for the future. I mean, we'll first do this. Yeah. Yes, so now I want to write down what this class does. For the group, yes. Yeah, but for this one you do. Yeah. So what I can do is I can write down a very simple map which goes from the group ring to itself. And for notational reasons, I will denote the generators of this group ring in this case by E gamma, because they will be the basis of a module later. dc of E gamma will just be pointwise multiplication by this cocycle. Yeah, this I will write down an unbounded class. Yeah, but there is, well, not a problem here, but the thing is that this co-cycle can have quite a big kernel. So, or it will have quite a big kernel, which we'll denote by gamma c. And if I multiply from the right by elements of this kernel, this map will be linear. So, yes, yeah. So the group structure on Z is addition, indeed. So. No, sure. You can do this and then take the generator of that one parameter group, and then. Yeah, it will be a one-parameter group of automorphisms on that algebra. Well, you will see. You can approach it from that way, and then what you get is a Kasparov module for the fixed-point algebra of this action. Yes. Yeah. So there is a restriction map by viewing this as functions. Take a restriction map from the group ring to the group ring of the kernel. And this you use to define an inner product on this thing with values in the reduced Schuster algebra of the kernel. And this gives you a C star module. Let me. Yeah, it's very big. So this is not. So you get this C star module, which basically, you just consider the elements of the kernel algebra as coefficients. And then this becomes a self-adjoint regular operator with compact resolvent in this C star module. Yeah. There's many ways you can view this. Yeah. It's a circle action on a C star algebra, and then indeed. So this is an unbounded Kasparov module. So this gives me an element in this KK group. Yes. Homology class of Z. Yeah, this is probably. And then you get this class, you say. But in this group, so I mean, how do you get the coefficients then? Maybe we should talk about this. It'd be nice to see. Yeah, in a way. So this class, although it's not living in the right group. But we can prove something about it. So if I have an element gamma and gamma, then I can take the unitary in the group algebra, and this gives you an element in the odd K group of gamma. And actually, in this case, this turns out to be an isomorphism with H lower 1, which is exactly generated by the elements of the algebra. Now you can prove that if, so the pairing given by the Kasparov product, almost. Wait, I should write it the other way around. Paired with this KK group, but since I have these funny coefficients, this ends up in K0 of the coefficients. take this U gamma and this DC, and indeed what I will get is the sign of the value of C at gamma times the class of the free module with these coefficients to the power the absolute value. And this is really extremely easy to prove because this module, you know exactly what it is free, and you can it's just a counting argument. So this behaves in the way you would like to do it. It's just that you have these coefficients, which you now want to get rid of. And this you can do. So gamma C is also a group of hyperbolic isometries, and therefore it satisfies the strong Baum-Kohn conjecture, and this means that there is a gamma element of index 1, which is defined basically using this space. So this is the easiest case. No, just H. Yes. So this is, again, a hyperbolic isometry group. And so we will use Kasparov's gamma element, which he constructs using the Dirac dual Dirac method. So this is a product of two classes. So we have a Dirac class, D bar, which it lives in the K homology of the Clifford algebra of H3, coefficients in C. And there is a dual Dirac class, which I don't know if there is a standard notation. Yes, that's what I mean, yes. As a Riemannian manifold. And there is this dual Dirac class, which you can unboundedly write as rho d rho, where I should put an x0 here. Yes, rho x0 of x is the Riemannian distance between x and x0, and you Clifford multiply by its derivative. And I want to use the unbounded version to take an explicit product. But it turns out that I have to, for my product to work, I have to modify this, this unbounded class a little bit. So what I need to do is I need to take another representative, but it's a very, it's a very minor modification. So I can take any number between 0 and 1, and instead of multiplying by rho, I multiply by rho to the s. I need to. Yeah. I need to temper this one. Yes, so you will see why this occurs. So instead, as a class, these things are the same. So I take rho s x0, d rho x0. And this is really a technical reason, which I don't think I will have enough time to discuss the details, but I'm happy to do that afterwards. So if you take the product of these two classes, then I get, I'm going to write this cryptically. I haven't used that yet. So this is the gamma element in KK. Yeah. So this has index 1 because these groups satisfy strong Baum-Kohn. So the index of this operator is 1. And you can view it in the way it's constructed. You can view this. Actually, there must be a C here. This works for any group, but I'm considering it for this specific kernel group because that's the group I want to get rid of. And I can view this now from the way it's constructed. Instead of viewing it in this equivariant group, I'm going to view it as an element in the K homology of the reduced C-star algebra of this kernel. And then what I can do is take the Kasparov product with this class here. And then since this has index 1, by this theorem here, this will have exactly the right behavior. But I'll write that out now. So the idea, take Kasparov product of this class DC that's up there with this gamma element class, tempered 1. Now, since this co-cycle module is so simple, it's really just a free module of it. I'm not sure if I understand what you mean by that. Yeah, oh yeah, that's what it is, indeed. Sorry? No. So there is another technicality that pops up here. Actually already popped up in the proposition about the index pairing. But for that to work, you actually need to assume that C is surjective. Otherwise, there is some scaling involved. So you can define the norm of C as the minimal number in the set of values. And then you normalize. This will have some consequences later. For the specific case of Bianchi groups, I can deal with this, but I would like to understand. Yeah. You can always do this. I mean, the image is always a free abelian group, so you don't essentially change anything, but if you want to get the right index behavior, this matters. Is that a term for it? So if you assume that, then you have short exact sequence of groups, and so under this assumption that C is 1, so call it normalized or something. And then you can write down a non-canonical splitting by choosing any element in the inverse image of 1, and then you can split the sequence by just mapping n to g to the n. And this will correspond exactly to choosing a connection on the module that I just built from this co-cycle. So, right, so this splitting induces a trivialization of this module EC, where it just becomes isomorphic to direct sum of this coefficient algebra over Z, where basically this just means you choose a basis corresponding to these elements E, G to the nth. And if I have this trivialization, then I can just write down the trivial connection. So in that picture, it's really simple. I need to, wait, let me first just take the simplest dense subalgebra. It will extend to something slightly bigger. So the connection, I'm going to write the connection relative to this unbounded module given by this gamma element. So that means I'm going to get the module again, but now I'm going to get forms which are given by commutators with this operator. And the map is just given by, should I write this? E g to the nth u delta goes to e g to the nth commutator with this operator. And this gives you a connection. You can write down a global expression using EC if you would like to do that. So nabla is a connection, and it commutes very obviously with the operator dc, because the operator dc in this picture is really just multiplication by n. So there's nothing fancy going on here. Question? No. So now we can, using this, we can write down the Kasparov product explicitly of these two elements. So we form the operator dc tensor 1 plus 1 tensor nabla v bar plus rho s d rho on the module EC tensored over C star reduced of gamma C with L2. Well, let me just write S bar there. So this spinor bundle, which is where this gamma element acts. And this should represent the Kasparov product. So this is a module over the group algebra. And this is just a Hilbert space. So the result is, though, this is not a spectral triple in the ordinary sense. But if you take its bounded transform, you will get a Fredholm module. So this pair and this is why I had to introduce this S. This represents the product of the class DC with the class D bar plus D rho. But the commutators, so note, the commutators of 1 tensor nabla, this Dirac bit is not so important. But if I take commutators with the group elements here, they are not bounded. But if I multiply them with power of the resolvent, so U gamma, and now I multiply this with, I need to give this full operator a name. Let's call this D. If I multiply it with this, then it will become bounded, and also from the other side. The resolvent is compact, that's not really a problem. And now it's important that S is strictly between 0 and 1. If S was equal to 1, this would still be true, but if you take the bounded transform class and you want to prove that this is a Fredholm module, then you really need this property here to prove that the commutators are compact. Well, you can say this is an unbounded class because this is sufficient to get a Fredholm module. So they're unbounded commutators, but they're tame in some way. They're not, you can control them. And exactly the same phenomenon I saw in some work I did on Kunst-Krieger algebras. If you compute this, there is some balancing going on between the values of the co-cycle and what these commutators do. And this is why it works. It's really quite nice. So we can write down this product explicitly, and from this result here, that if I pair the bivariant class, I get exactly the free module of the right rank with the right sign. Since the gamma element has index 1, this will now give you that the index pairing of these classes is actually doing exactly what you want. So the index pairing K1 C star reduced gamma cross K upper 1 C star reduced gamma into Z is now compatible with the homology cohomology pairing. So this is the index pairing, and this is just evaluation C gamma. And this is the way it was made. So yeah, if we call the class we constructed here, so symbolically you can just say this now really maps to the right thing. There is something funny about this map, because this normalization procedure forces you to actually, this class C is in fact, it will be the class of the norm, and then you have to normalize the first operator from the module. So tensor 1. Doesn't really matter actually if you normalize it here, but you have to multiply it by the multiplicity. And this means that if you look at this, you would like this map to be a homomorphism, but this is, or at least not to me, it's not really clear how to prove that in general. But for these Bianchi groups, since we know the full K theory and K homology, in that case, this map is an isomorphism. And for that, you use some universal coefficient type argument, and I would like to improve that actually. Somehow I would like to see that this always works instead of using these special properties. Because that would give you, in the construction, well, I mean, I heavily rely on Baum-Kohn being true, but other than that, it's really, this should work for any hyperbolic isometry group. Okay, so now recall Gießen sequence, 0, 0, C0 of M, cross product in the middle, this here goes to 0, and now we've constructed these classes. C here and this map here It's just a restriction map because the reduced C-star algebra sits inside this cross product. So if I have a cycle here, I can restrict it to the reduced C-star algebra and get a cycle there. But in this case, because of the structure of this thing here, I can actually pull these cycles back easily. And the way you do that is you choose just one point on the boundary, and you move it around by the group. And since the orbits are dense, this gives you faithful representation. So by choosing some x in P1 of C, one gets a representation pi of x of f. I only have to represent. So in order to do this, recall that these classes defined on this tensor product of the module with some L2 space. So if I can represent the functions on this module EC, then I'm fine. And the module EC was just a completion of the group algebra. So I can just tell you what should happen on a basis vector. And what you do is just this. And this gives you a covariant pair. So I think this is used by lots of people that construct C-star algebras from dynamical systems. So you check that this representation of the functions on the boundary is compatible with the representation of the group, and so you get a representation of the cross product. And this gives you a way to pull back these cycles here. Right. Oh, yes, of course. Sure, yeah. Yeah. This is what Emerson and Nika do on the boundary of the Cayley graph. Uh-huh. This is a very interesting question, which I haven't gone there yet. But Emerson and Nika do this on the boundary of these Cayley graphs, and in they don't do it for this type of groups. No. They do it for hyperbolic groups and for the action on the graph, really. Yeah. So this is actually, I'm going to say something about that now. So they use the Patterson-Sullivan measure to get this class. And something similar is going on here. And also in the case of Kunz-Krieger algebras, you can do this. You can actually prove there that all your Fredholm modules can have finite rank commutators. But it would definitely be very interesting to aim for such results here as well. No, in the Kunz-Krieger case you get, yeah. No, but here you would get some dimension, some Hausdorff dimension thing. Yeah. So no, I didn't erase it. So this is also related, your question, to this first map in the sequence, because this, the map, so what is it? Yeah. DK1 is basically given, I'll put hyphens, by the product with the extension class this extension cross products. This you can call the boundary extension. And this class, let me see how much time I won't go into detail because I also want to say something about Heck operators. But for those of you who know, there is a certain measure on the boundary here, and you can use that measure to find an explicit representative of this class in this bivariant group. Yeah, so what you do is you make a module out of H3 with coefficients in M. These are the compacts here. C0 of M sits here. I mean that I'm not completing this as a Hilbert space, so I start with some compactly supported functions, but then I define an inner product with values in this function algebra. So this, yes, yeah. So because this extension in another model of KK theory, this extension defines a class in the KK group of this algebra with coefficients in this algebra. And this is Morita equivalent to the quotient, so you would like to find a cycle representing that class. Now, the way you do this is take the compacts here, and you can define another guy by just adding the boundary. And what you get is, again, C0 of M. But now, on this thing, the way I made it is a bit cheap, so you have a representation of the boundary cross product here. And now there is an isometry of this module into this module, where here, to build this module, you use the measure on the boundary. You get an isometry here, which behaves well with respect to these representations, and then you get, you define P to be VV star, and that projection will represent this boundary extension. I don't have time to go into further detail, but we can talk about it more if you want. It's actually quite beautiful construction. But so this really uses this Patterson-Sullivan measure that Günther also mentioned. Yes, somehow, yes. And because that helps you to describe this map here. Yeah, I must say I don't have a full understanding how it looks, because then you have to take products with this class, and we're still working on. Yeah. But I would like to have a nice unbounded class here, actually. This would be the best, from my point of view. No, I don't really care about that right now. This is a question for later. So that's how you do that. Now let me very briefly say something about the Heck operators. So I have this subgroup of PSL2C, and then you can write down the commensurator, which are those G in the big group, such that as finite index in gamma and G, gamma G inverse. If you, for such elements, so this is quite a big group, and there are some theorems about if your group is arithmetic, then this is actually a dense subgroup. And on homology, what you can do when you have these, when you have such a group element, write down a Heck operator, which goes from H1 gamma to H1 gamma. Should give it a name. Let's call it HG. The way it's defined is you start in the big group, you restrict to this intersection. It's the cohomology of the group. Yeah, sorry, Z. Yeah, suppressing that. I do the simplest thing you can think of. Just no, no, no. No. So, no, no, no. I'll suppress the z's here, just to save space. But the coefficients are just the integers, or maybe 2 copies. You can do it there as well. Now here there's an isomorphism. Yes. No, and then the last map is a transfer. So this is a co-restriction map. So you go back to gamma. And this is, of course, the intricate map that you use. Here you use the finite index property. So you choose some cosets, representatives, and then you can map any element in the small group. In the big group, you can associate a unique element in the small group by choosing these cosets, and that's this map. I don't have time to do this in detail. The point is that all the maps in this sequence can actually be implemented on the level of KK theory, because, well, this is just, the first 2 are easy because they come from group homomorphisms, so you get algebra homomorphisms. And the last one you can use in a very similar way. So for the transfer, yeah, it's just a finite projective module because this thing has finite index, is implemented by some KK cycle. I really don't have time anymore. So let's see, how should I wrap this up? We're sure we can prove it, but we're writing it down. And that's that the isomorphisms here from this Giesian sequence to the homology groups will be Hecke equivariant. So you have, again, I haven't given you detail, but the Hecke operators exist on the level of K theory. Also, you can, in the commutative setting, you use coverings. They're finite coverings, so you use wrong-way maps. And the maps to the homology groups that I described earlier, they will respect this Hecke action. So you really get an isomorphism of Hecke modules from group homology to K homology. And this will, this was quite some work to prove, but this will be a starting point for us to further investigate. And now my time is up. Yeah, this has been our aim. In a sense, I'm quite happy with this co-cycle construction, but initially what we wanted to do is if you have some mass form, you get a distribution on the boundary. And our original aim was to construct K-cycles using those guys. And this I will think about in the future, but this turned out to be difficult. Yeah, yeah. Yeah, 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 in this case, yeah. Yes, yeah, yeah. It's an agoric action. Yes, but you can do similar approach there. Yeah. That's the usual way to do it, but you can do the cross product there for the full boundary as well. Mm-hmm.
by associating to a cusp something which doesn't depend on the rest of the geometry. And writing a kind of formal difference, it was removing the cusp.
Mm-hmm.
And this has obvious meaning in geomology, but I don't think it a paper of Lachaud, which is, I think, 78.
Okay, I will look this up.
In which, he was, and I'm sure it has a lot of potential for this type of thing, because essentially what he was doing was going back to the compact case by doing this abstraction of the cusp. And the cusp, for the cusp, he had the unit model.
I will have to read this. Yeah, definitely. Yeah. Yeah. Yes. Yeah. You can write down the same thing here, but I don't know. I don't know this, but this may be known. I mean, you can write down the same formula. I wonder if Sullivan or someone should have considered this. Yeah, no, yeah, I'm aware of this. I mean, yeah. No, in the end, you would like to go. I mean, in a sense, this is the reverse engineering direction to learn to understand this. But in the end, I mean, this is what you really want.